Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about public goods with punishment. My name is Rick, and my co-teacher, who originally prepared these notes, is Christoph. So let's get an outline of what we're going to cover today. We're going to start by talking about the public goods game, and that will set up the problem of cooperation, which is an interesting problem to look into. And we'll look at whether something called peer punishment can be used to solve the problem of cooperation. To find that out, we'll use a new technique called, well, I'm going to call it Pairwise Invasion. And we'll look at that by comparing pairs of strategies. We'll compare defectors versus cooperators, cooperators versus punishers, and punishers versus defectors. Once we've done that, we can put it all together and create something that we'll call a pairwise invasion graph, and that'll give us a perspective on an important solution concept in evolutionary game theory, and that is called the Evolutionary Stable Strategy, or ESS. And finally, we'll make a note about applying ESS, or how it can be applied in economic game theory. So that's quite a bit to get through, so we'll get started. Let's start with the public goods game. So I'll just go through it very briefly because we've covered this before. The essence of it is that there is a group of N players, and they have two strategies. They can either be cooperators or defectors. The cooperators contribute cost C to the public good. The defectors contribute nothing. The public good then grows by some factor R, and let's say R is between 1 and N. And as we've seen before, that makes cooperation a problem, as we'll see again in a minute. Once the public good has grown, then it's distributed out to all the group members. So that sets up the problem of cooperation. And what I mean by that is cooperation is a costly effort, and it's not clear that it's rewarding. Why is that a problem? Because we see these kinds of scenarios all the time in nature, and yet cooperation does occur in them. So how has nature and how have people solved this problem? And that's what we'll be trying to figure out for the next little while. So to look at this formally, we'll let X be the number, the frequency of cooperators in the population as a whole. So when we sample individuals to play the game, we'll sample N individuals from this whole population. They'll play, and we'll figure out what the fitness to the defectors are and the fitness for the cooperators. The defectors, if I look at all the other players in the group except myself, and I'm a defector, then I will see X times N minus 1, because there are N minus 1 individuals in the group other than me, and there's a probability X of each of them being a cooperator. So X times N minus 1 is the average number of cooperators I can expect to see amongst my co-players. They will each contribute C, so that's how much of the resource goes into the public good. It will be multiplied by a factor R and divided by all the players in the current game. So that gives me the fitness for a defector. What about for a cooperator? They will also see X times N minus 1 cooperators amongst their co-players, but they are also a cooperator. So they'll see one more cooperator on average. Times that by C to get the total contribution, times it by R to get the growth factor, and split it amongst everybody. And don't forget that as a cooperator, I had to pay a cost C, and there we get the fitness for a cooperator. And if you check the math, you'll see that that is less than the fitness of a defector. And because cooperators always get less than defectors, they will become less common in the population, and the population will converge to all defectors. And that's the essence of the problem. How can cooperation evolve in this kind of setup? How can it be started? And how can it be sustained? Today, we'll look into the possibility of peer punishment, allowing cooperation to evolve. So what we'll do is we'll add a third strategy, and they are peer punishers, and we'll call them Big P. So how they work is they cooperate, just like C does, but they also do something else. They impose a fine beta on each defector at a cost gamma per defector. So they have to pay for every defector they see, they have to pay a cost gamma. And what that does is imposes a fine beta on the defector. So punishment is costly, and the more punishment that's needed, the more expensive it is. On the other hand, the more punishers there are in a group, the more a defector is going to be punished. So generally, how would we go about solving this kind of thing using the replicator equation? Well, we would let Y be the frequency of punishers, And just to complete that, if x is the frequency of cooperators and y is the frequency of punishers, then 1 minus x minus y is everybody else, which is the frequency of defectors. And the only thing to keep track of there is to be aware that x plus y have to be less than or equal to 1, just so that the frequency of defectors is always 0 or positive. And of course, the x has to be bigger than or equal to 0, and y has to be bigger than or equal to 0. So the general solution for any x and y would have to be a solution in some xy space. So x would go between 0 and 1, y would go between 0 and 1, and x plus y would be less than or equal to 1, and we'd get this region here, and we'd have to solve for the dynamics in that entire region, and that is a hard thing to do. Too hard for this class. So instead, we're going to cheat a little bit. We're just going to consider mixed populations of 2 types at a time, and then we're going to infer something about the whole population and the general result from those all possible pairs. So we're going to call this technique Pairwise Invasion, and we'll start by looking at defectors versus cooperators. So the basic idea is to assume that there are just 2 types in the population, just D's, defectors, and cooperators, and there are no punishers. In other words, we're going to assume that y is equal to 0. Then we'll use the replicator equation, which is just dx by dt is equal to x times 1 minus x times fc minus fd, where we already saw, when we were looking at the problem of cooperation above, we already saw that fc is always less than fd. So we already know that dx by dt looks like a smile. It's always negative between 0 and 1, which means x is decreasing. We have an unstable fixed point at x equals 1 and a stable fixed point at x equals 0. So we're going to draw this as a graph. And what I mean by graph is a network. We're going to have nodes and links. In this case, we've got a very simple case. We've only got 2 nodes, and I'll draw them as, I'll put letters inside of circles. And what I mean by that is x with a circle around it is a population of all x's. And then I'll draw lines between them. And what I mean by that is a mixed population of both types. And the closer you are to the 1, the more dominant or prevalent that type becomes in the population, the higher its frequency. So on top of this, we can lay our arrow that shows the direction that the dynamics are going to move. So this point here, x equals 0, represents a population with only defectors. So it matches this, D here. And x equals 1 is all cooperators, so that matches this. So we can draw an arrow in the same direction as we have on our rate graph to get an idea of how things will tend to evolve over time. So that case was just looking at defectors versus cooperators, which we've seen before, and we already know that defection takes over. What about including the punishers? Again, we want to look at this in a pairwise manner. And in this case, let's look at cooperators versus punishers. So we'll look at the limiting case of just C's and P's with no defectors. What this means is that x plus y is the whole population. And again, we can use the replicator equation. Let's do it for punishers. dy by dt is equal to y times 1 minus y times, what goes in here? The type we're looking at, fp, minus the fitness of the other type, which is this time C, FC. So we need to figure out what FC and FP are in this case, where it's just punishers and cooperators. Let's work out the fitness for a cooperator. The punishers also cooperate, so everybody in the group is a cooperator in this sense. They all contribute something. That something all gets multiplied by R, then divided by N, and don't forget the cooperator has to pay a cost C. What about the punisher? Fitness for a punisher. Well, again, everybody contributes. Again, they contribute C, and it's multiplied by R. All of that, again, is divided amongst everybody. These punishers, since they're just like cooperators, they had to pay the cost C, and they also have to pay a penalty to punish defectors, and it's proportional to how many defectors there are. In this case, there are no defectors, so there's no cost there. And because of that, the fitness to a punisher is exactly equal to the fitness of a cooperator. So dy by dt is y times 1 minus y times 0, which means dy by dt is 0 everywhere. And that's a strange case. That means there is no selection acting on cooperators versus punishers. So let's draw our graph for this. Sorry, first I'm going to draw my dy by dt. Over here we have y equals 0 and y equals 1. And what we see is it's 0 everywhere. That means every point along that axis is neutral. There's no drive, nothing driving the population towards or away from any one of those points along that axis. They're neutrally stable. And again, we can draw a graph from that. C with a circle means a population of all cooperators. P with a circle is a population of all punishers. And between them, we just have a line of neutrally stable points. We have one more comparison to make. We haven't looked at punishers versus defectors yet. So now we'll consider a population of just punishers and defectors, no cooperators, meaning x is 0. Again, we can write down the replicator equation, and it is y times 1 minus y times f of the type we're interested in, fp, minus the fitness of the other type, fd. So what are those fitnesses? Let's look at the defectors first. The first question we need to ask is how many people in the group contributed. As a defector, I know I did not, but of the remainder, there are n-1 other people in the group. A fraction y of them will have contributed because they're punishers. They each contributed an amount c, which is multiplied by r. Then this whole amount is shared amongst everybody. But now the punishment comes into play. Each of those y times n-1 punishers find the defector by an amount beta. What about the punishers themselves? Again, they will see y times n-1 other punishers or contributors in the group, and they are a contributor themselves. Everybody contributes c, which is multiplied by r, and shared amongst n individuals. As a punisher, as a contributor, they have to pay a cost c, and because they're punishers, they have to punish all the defectors they see in the group. So how many do they see? Well, there are n-1 possible defectors in the group. Y of those are punishers, and 1 minus y are defectors. And those defectors have to pay or cost the punisher gamma. So this bit here is defectors being fined by punishers, and this is punishers paying a cost to fine the defectors. So in the end, what we're really interested in is the difference, FP minus FD, and I'm going to write down the kind of final answer to this, or at least an intermediate step. You should work through it yourself to make sure that I got it right and that you understand how to do it. So what it turns out to be is there's a leading term, which is minus 1 minus r over n times c minus gamma times n-1, and that's all a constant term. And then there's another term which depends on y, which is beta plus gamma times n-1 times y. And if you look at this carefully, you will see this stuff is all negative and this stuff is all positive. So that gives us a good hint about what's going on here. When y is very small, then this second term is tiny. It goes away. For example, if y equals 0, then it's entirely lost. And all we're left with is this leading term, which is a negative constant. So that means dy dt is negative, because this whole thing is negative, when y is near 0. But then as y grows, this whole term grows too, and for some value of y, it's going to cross 0 and become positive. So it's important for us to understand when that occurs, because that's when the behavior of dy dt changes. It changes from being negative to positive. So this happens at some point, we'll call it y star, and it just turns out to be this leading term, but the opposite sign, divided by this factor in front of the y. And you can check that for yourself. Okay, so y star turns out to be then a positive number divided by a positive number. So y star as a whole is bigger than 0. But what we don't know yet is if it crosses, if dy dt crosses 0 somewhere between y equals 0 and 1. Is y star smaller than 1? So we could check that just by putting the condition y star is less than 1 and looking at what the consequences have to be. If I want this to be less than 1, what do I have to set? There's all sorts of ways you could write that condition. I'm going to write it like this. Beta has to be less than some value, beta min, let's call it, which is equal to, or let me say is defined as 1 minus r over n times c, all divided by n-1. So, oh, what did I just write here? That's weird. I wrote beta is less than that. Sorry, that's wrong. What I meant to write is beta is bigger than that. So what's the upshot of that? What this means is that there is an interior fixed point, some y star, between 0 and 1, if this fine beta is large enough. Okay, that's enough to tell us what we need to know to draw our graph. So what we've got is that there are two cases to consider. Either beta is less than this minimum amount, or beta is more than beta min. So if it's less than beta min, then there are no interior fixed points. We already saw that FP was less than FD, so that means when y is small, dy dt is negative, so it has to be a smile again, which means the population is driven towards having zero punishers. That's a stable equilibrium, and there's an unstable equilibrium with all punishers. So let's draw a graph of that. Population of all defectors and a population of all punishers, and we just have an arrow from punishers to defectors. That's the direction the dynamics would take. On the other hand, if beta was bigger than beta min, then again, dy dt would start negative, but at some point it would cross 0, and again it would cross 0 there. And this point would be y star. So when we're smaller than y star, then y is decreasing, but when we're bigger than y star, then it's increasing. And because of that, we have two stable equilibria and an unstable equilibrium in the middle. And again, we can draw a graph that kind of captures that. Population of all defectors versus a population of all punishers. In the middle, there would be an unstable equilibrium, and we'd be driven away from it, to one of these populations of all defectors or punishers. So what we've done so far is put together pieces of our graph, our network, and now we can put it all together into something, let's call it a pairwise invasion graph. It's got a nice acronym. So the way we want to do this is we'll draw all the pure population states as nodes in our graph. So that would be all defect, all cooperate, or all punishers. And then we'll use the arrows that we worked out to show the evolution. So for this situation that we're handling, we have to be aware of both cases that we've looked at. And those cases, again, are when beta is less than this parameter we found, beta min, or when beta is more than beta min. And we need to draw our three pure populations, all D, all C, and all P, for both cases. And now let's go back and look at these and fill in the arrows. Okay, the first case we can look at is the arrow between D and P, or the link between D and P. And there are two possibilities. If beta is less than beta min, then we have an arrow from P to D. And on the other hand, well, actually, let me just draw that in first. And on the other hand, if beta is more than beta min, then we have an unstable equilibrium in between and arrows pointing away from it. And let's look back further. Okay, here's another case. We have the nodes C and P, and the link between them is just a line of neutral stability. And that's true for both cases. And the first one we looked at was the link between D and C, and we saw it was just an arrow from C to D. Okay, so this doesn't tell us the full dynamics for any population structure. It only tells us about transitions between pure populations. So populations of all one type, whether they will can transition to populations of another pure type. But it does help us to understand the evolution of the system. And the important thing to notice is that it shows us which states or strategies can or can't be invaded. So that ties into a concept we've already seen, which is the evolutionary stable strategy, or ESS. And an evolutionary stable strategy is a strategy or a type that is a stable equilibrium when it's adopted by the whole population. So it can't be invaded by any other strategy. How does that show up in our graph? All pairwise invasion arrows point in towards that ESS. So in the case here where beta is less than beta min, we have one strategy here which has all the arrows pointing in. That's the D, all defect state. So that is an ESS. In the other case where beta is greater than beta min, then we have arrows pointing into D still. So again, that's an ESS. But what about P? Think about that. I'm going to just write down what we've said already. So let's try to answer that question. Is P an ESS in the right-hand graph? Well, it's got an arrow going into it. It doesn't have any arrows going out of it. So that seems promising. But no, the criterion for an ESS is all arrows have to be pointing into it. So we've got this neutrally stable line here, which means there's no evolution or selection towards or away from P. It's just neutral. But that's not enough to make P evolutionarily stable. And the reason that's not an ESS is because the population may stay near all punishers for a long time, but eventually it's going to drift to being all cooperators. And once it does that, then selection kicks in, meaning that there's an arrow actually pointing towards something else, and that something else is all P. So it'll evolve towards all P, and it'll stay there. So what have we learned from that? We've learned that peer punishment can prolong cooperation if the fine is big enough, but eventually the defectors will still take over. So peer punishment can't protect a public good. And the reason is that what we might call second-order free riders, which they're not as bad as first-order free riders, which are the defectors. So they are contributing to the common good, but they're second-order free riders in the sense that they're not contributing to the punishment. So these are the cooperators, and having them present in the system undermines the effectiveness of punishment. So we might imagine we're starting with a population of all punishers, but just through neutral drift, we're going to slide away from that. There's going to be cooperators emerging in the system, and nobody pays a cost for punishing because there are no defectors, but eventually we'll get to a case where there's all cooperators. And when we do, then there's no punishers left over to prevent defectors from breaking into the system. And so we'll quickly collapse to a population of all defectors. So the last thing I want to mention is the relevance of ESSs and maybe these pairwise invasion graphs in economic game theory. So we developed these concepts, the ESS and this graphing technique, PIGs, from evolutionary game theory. But I want to show that they're also relevant to economic game theory, at least in the case where you have symmetric games. When we first developed evolutionary game theory, we made the connection between fitness and payoff, and we said that fitness was basically the payoff. Now we can reverse that and recognize that where we're using fitnesses, we could just as well be talking about payoffs. Then in these pairwise invasion graphs, these states of all one population means if everybody else plays X and the arrows show preferences, i.e. what I should do. So you can read something like X, arrow in from somewhere else. That would mean if everybody else plays X, I should play X. And an arrow out, like X goes to Y, would mean if everybody else plays X, I should play Y. And note, everybody is going to be thinking like that. So it's reasonable to expect that the arrows actually show transitions in strategies of the whole, of all the players in the game. So that means that the arrows actually show rational decision making. If we have a population of all X, and every player then thinks, well, in that population, I should switch to Y, then the whole population, every player, rationally, will switch to Y. So we can use these pairwise invasion graphs to kind of get a sense of how people are going to make or come to conclusions about what strategy to play. If they think along those lines, if everybody else plays this, then I should do that. Then we'll arrive at nodes that only have inwards arrows. Once players have reached those nodes, they will no longer switch out of them. So those nodes are ESSs, where there's only arrows pointing in. And if nobody can improve by unilaterally switching out of those nodes, then they're also Nash equilibria. So every ESS is a Nash equilibrium, but not every Nash equilibrium is an ESS. So if we have the set of all ESSs, then that's just a subset of all Nash equilibria. There's my little Venn diagram. Okay, that was a lot of material. Let's just review. We talked about public goods games, which let us set up the problem of cooperation. We introduced peer punishers to see if they could stabilize cooperation, and they pay a cost gamma to find defectors by an amount beta. Then we looked at pairwise invasion between these pairs of pure populations or strategies, D versus C, C versus P, and P versus D. That gave us the preferences along the edges of our graph, which let us draw the full pairwise invasion graph. And by having the pairwise invasion graph, we could see what the dynamics were, and most importantly, we had a new perspective on evolutionary stable strategies. And in this case, we found that all defectors is still the only ESS, So peer punishment on its own cannot maintain cooperation. And our last point was just about looking at ESSs and more generally pigs in economic game theory. And I made the argument that these are relevant concepts in economic game theory. Well, that's all for this lecture. Thanks for watching.